my video. In this video, we'll explore the world of limits through Zeno's paradox. Oh, by the way, my name is Nadia Herianto. I'm from Indonesia. I'm currently in grade 11 and I study in SIS Kelapa Gading. Now, upon hearing the phrase Zeno's paradox, a lot of you might be wondering, who's Zeno? And what's a paradox? So, Zeno of Elea was a Greek philosopher and a logician. He was born in 495 BCE and was famous for his paradoxes, which helped develop a lot of mathematical concepts that we have today. On the other hand, paradoxes are statements that we all know is wrong, but its explanation feels very true and logical. This paradox is also known as the paradox of Achilles and the tortoise. So, Achilles allowed a tortoise a head start of 10 meters in a race. Both started running at a constant speed. Achilles at 10 meters per second and the tortoise at 1 meter per second. After how many meters would Achilles take over the tortoise? Zeno suggested that it would be impossible for Achilles to take over the tortoise. He divided the path into points A, B, C, D, and so on, where points A and B are 10 meters apart, points B and C are 1 meters apart, points C and D are 0.1 meters apart, and so on. He suggested that every time Achilles reached the point where the tortoise has started, the tortoise has run to the next point. Therefore, no matter how long they run, Achilles will never catch up with the tortoise, though the distance between them will keep decreasing. We all know that since Achilles is running at a speed 10 times faster than the tortoise, he sure will overtake the tortoise. It's just logic. But Zeno's suggestion seems logical too. This leads to the question, what is wrong with Zeno's explanation? To help us analyze this problem better, let us first list the distance between the consecutive points. We have 10, 1, then 0.1, then 0.001, and so on. Now that we have it written down, do you see any pattern? As you can see, 10 times 0.1 is equals to 1. 1 times 0.1 is equals to 0.1. And 0.1 times 0.1 is 0.01. Since we just need to multiply the last term by 0.1 to get the next term, we can say that 0.1 is the common ratio, which means that the distance between the consecutive points form an infinite geometric sequence. Before we move on, let us first discuss sequences and series. In mathematics, sequences is a list of numbers that are in order. Sequences can be finite or infinite. There are many different types of sequences, such as arithmetic, geometric, triangular numbers, and many more. A geometric sequence is a list of numbers that have a common ratio. That is why the sequence 10, 1, 0.1, 0.01, and so on is an infinite geometric sequence. As for series is just the sum of an infinite sequence. So if we have the infinite sequence 1, 2, 3, 4, 5, and so on, the series derived from the sequence will be 1 plus 2 plus 3 plus 4 plus 5, and so on. The formula to find the sum of a geometric sequence when the common ratio is not equal to 1 is S sub n is equals to a sub 1 times 1 minus r to the power of n all over 1 minus r, where s is the sum of the terms, n is the number of terms, a sub 1 is the first term, and r is the common ratio. By replacing a sub 1 with 10, r with 0.1, and n with infinity, we get s sub infinity is equals to 10 times 1 minus 0.1 to the power of infinity all over 1 minus 0.1, which is equal to 10 times 1 minus 0.1 to the power of infinity all over 0.9, which is also equal to 100 over 9 times 1 minus 0.1 to the power of infinity. Hold up, we now have a problem. How do we find 0.1 to the power of infinity? Surely, we can't keep multiplying 0.1 by itself because we'll have to do it an infinite number of times. Worry not, guys, because this is where the concept of limits becomes super useful. Simply put, limits is about finding something that we can't directly find. Just like finding 0.1 to the power of infinity. This is because limits is not about the answer itself, but about what happens as we get closer and closer to the answer. Before we use limits to compute 0.1 to the power of infinity, we need to first understand the limit language. This is the basic limit notation, and it is read as the limit of f of x as x approaches a is equal to L. X arrow a means as x approaches a, f of x is just any function, and L is what the y value of the function is getting closer to. Now, let us try find the limit of 0.1 to the power of infinity by multiplying 0.1 with itself multiple times. 0.1 times 0.1 is 0.01, 0.01 times 0.1 is 0.001, 0.001 times 0.1 is 0.0001, 0.0001 times 0.1 is 0.00, and so on. As you can already see, as we keep multiplying, the answer we get becomes smaller and smaller and smaller. And if we do this process many times, we will get a value that is very close to 0. Now, as what I've said, limits is not about the answer itself, but about what happens as we get closer and closer to the answer. Thus, we can say that the limit of 0.1 to the power of n as n approaches infinity is 0. Back to our working for finding the sum of the geometric series. By substituting 0.1 to the power of infinity with 0, we get 100 over 9 times 1 minus 0, which is equal to 100 over 9, which is also equal to 11 1 over 9. And 11 1 over 9 is approximately 11.1 to 3 significant figures. Therefore, we can conclude that Achilles will take over the tortoise after running approximately 11.1 meters. Now that we've got the distance, let us now find the time it will take for Achilles to take over the tortoise. As most of you should have known, the formula for time is distance over speed. The distance is 11 1 over 9 meters, while the speed is 10 meters per second. After dividing it, we will get 1 over 9 seconds. Thus, it can now be concluded that Achilles will take over the tortoise after running 11 1 over 9 meters and will do so in 1 over 9 seconds. From this, we can also now know that Zeno's analysis was wrong because he assumed that just because there is an infinite number of terms, the sum of the terms will be infinite. This is a misconception because there are two types of infinite sequences, divergent and convergent. Divergent sequences diverge, or do not approach to a real number. A geometric series is diverging if the absolute value of its common ratio is larger than 1, and its sum to infinity will be either infinity or negative infinity. Some examples of diverging sequences are 1, 2, 4, 8, 16, and so on, 1, 0, 1, 0, and so on, and 1, negative 2, 3, negative 4, 5, and so on. On the other hand, convergent sequences converge, or approach to a real number. A geometric series is converging if the absolute value of its common ratio is smaller than 1, and its sum to infinity can be found using the formula S sub infinity is equal to a sub 1 over r minus 1. As you may have noticed, this formula is the simplified version of the formula we used before. Some examples of converging sequences are 1, 1 over 2, 1 over 3, 1 over 4, and so on, which converges to 0, and 2.1, 2.01, 2.001, and 2.0001, which converges to 2. That's all for me today. I hope you enjoyed watching the video and learned something from it. See you next time. Bye!